Assalamualaikum warahmatullahi wabarakatuh. Perken- Let me introduce myself. My name is Ahmad Nur. You can call me Ahmad. My NPM is 22068262280. Today, solve. I'm going to explain my exam on mechanical fluids using day 5. First of all, uh, from because I already write a few of them here, I already work and the record failed. So I'm sorry for inconvenience. And let's start solving the problem. We had 5 problems and we tried to solve it using day 5. So, okay, from the questions, I'm from mechanical engineering. And from the exam, we found a problem about flow through an orifice meter, an airflow rate of up to 1 m 3 per s as a standard condition as expected its 0.25 diameter dug on orifice meter is used to measure in rate of flow. The manometer available to make measurement has a maximum range of 300 millimeter of water. Determine the diameter of orifice plate that should be used with D and D per 2 pressure taps. Determine the head loss if the flow area at the vena contractor is 0.65 of the orifice diameter. So, from what do we get here? Uh, Before we start to solving the problem, we need to stay conscious so that our mind is focused. Our mind is focused on solving the problem. Uh, okay, first of all, in day 5, there is 4 steps. There is intention, initial thinking, idealization, and instruction. First of all, intention. Intention of the problem is finding the orifice diameter for an airflow at 1 meter cubic per second. So, and the second problem is determine the head loss of the orifice diameter. And the third, we solve the problem in the name of God, the name of Allah. So we next move to the next step is initial thinking. The given data equals airflow rate is 1 meter cubic per second, and the maximum range okay, the maximum range is 300 millimeter of water. We assume the initial thinking step. We assume that the airflow is steady and the air can be treated as incompressible fluid. So the equation we get from the assumption above is that the orifice, we using the equation orifice coefficient. So here is the equation. This is the equation. If you see it, this is the equation. So now we move, that was the first problem. So we move to the second problem. We identified using pictures that the flow, this is A1, A2 is a vena contracta. So the given data about this problem is the given data is 0.65. Okay, 0.65. Okay, the given data is 0.65. A1. A1 equals 0.65. Okay, so from this picture, there is a water flow, a water that's flowing on the pipe. There is a gap between the pipe, causing the water to be squished and released from the outside of the two. This is the phase 1, phase 2, phase 3. From the phase 2 and phase 3, they going to expand quickly to make sure the pressure is released. So from the picture, we get assumption that A1 V12 equals A3 V23. So, and we neglected AZ. So equation we get is HR equals P1 minus P3 P. P1 P2 minus P minus P2 is the equation. And is the step. From the data we get that we assume that V equals 0, uniform flow to these two this is 2, this is 3, is uniform. The pressure is uniform across. Okay, I will neglect the friction force. There is no friction on the pipe. So the equation is F S X FSX equals FB plus FBX equals A plus FBX equals D per dt integral C V UP dE dA, sorry, dA. We simplify the problem using the assumption we use. So we get P3 minus P2 equals B2 minus B3 PQ per A1. So we already create assumption to solve the problem. So we begin to step 3. The step 3 is idealization. Idealization. Okay, we next get to the analysis process. So we going to solve the first problem. The first problem is that because we need to search pressure, M equals M dot CO AT equals 2P minus P1 minus P2 1 P4. This is the equation. So what we need is search the P2 P1 minus P2 equals 1 minus B4 per 2P equals M dot COAT quadrat. So T equals 1 minus B4 per 2 per 2 per 2 Q minus CO2 quadrat. Because the air density, there is air density of water is equals 153 kg per meter cubic, and air viscosity equals 1.46 times 10 5. So we need to find the Reynolds. So the RE D1 equals P V D mu equals K per mu equals K per D1. With the Reynolds number is 4P4Q mu P mu salah using mu P D1. So we insert those. So we get 1.23 per 1.46 times minus 10 square minus 5 times 4 times 1 equals P times 0.25. The equation we get is 3.5 times 5. This is the equation for RED1. So the next step is we search for the P1 minus P2 value. So the P1 P2 value, P1 minus P2 value equals P1 minus B pangkat 4 2 equals Q per CO AT square. So we begin to solve the problem. Solving the problem is that P is 1.23, 1 minus B is 0.7, 0.7 minus per 2 times 1, 0 CO is 0.625 times P4 and 0.175 square. So the result is we get is 2070 PA. After we get the value, so what we need is we need to find the h. The h is P2 minus P1 equals G P1 pressure water equals 2070 PA per 9.81 times 998. That's the pressure of water. So the result we get is 211 milliliter. So what do we get from this instruction? Is that the pressure one and pressure one minus this is what we get from solving number one. To solve number one, this is to solve part one. If you all forget, the part one is this. Find the orifice diameter for an airflow at 1 meter cubic per second. So we get is the pressure is 2070 PA. So the pressure we get is 2070 PA and height is 211 millimeters. But which is lower the maximum, the difference, the second guess will be made using smaller orifice diameter of 0.15 meters that corresponds to a beta of 0.6. The orifice coefficient at its diameter ratio is 0.615. The same calculation above. So this is what we get, but this result is the lower maximum pressure difference. The second guess we made is smaller orifice diameter. So this is this is lower than the maximum pressure differences at second guess will be made using a smaller orifice diameter of 0.615 meter, which corresponds to the beta of 0.6. The orifice coefficient at this diameter ratio is 0.615. The same calculation as above are carried out as, and the result pressure difference and manometer height is we make using the same, but because we make it smaller, causing the pressure gap is increased and the height is increased too. So what do we get is the final design. Final design 450. This is the same way. This is the same, but we use a different data using diameter. Okay, we now go to the second step, the second problem. The second problem we had is that from the equation above, we can start by using search about because from the data above, V3 equals V1. So we need to find a V2. So because we need to find V2, we write it that P3 minus P2 equals V2 minus V3 PQ per A1 is, and when we need to find V2 equals Q per A2. So Q 0.65 AT, because AT is 0.65, the given data from above. So the Q is 0.65 b quadrat a1. So we begin to insert the problem, begin to insert it. So we get p3 minus p2 equals p q quadrat square 1 equals 1 0.65 beta quadrat equals minus 1. So what we get is we insert the data. P3 minus P2 equals 1.23 times 1 square times 4 square per P square times 1 0.25 cubic times 1 equals 0.65, 0.66 square minus 1. So the result we get is 2019. 1290. This is the result for P3 minus P2. So the next step we get is that from the above, to solve, to find HET, HER, we need to find, we need to substitute using this equation. So the HER equals P1 minus P3 equals P1 minus P2 minus P3 minus P2 equals P. We insert the data. P1 is 2,830 minus 1,290 times m cubic per 1.23 kilogram. So the result we have is 1,250 Newton meter per kilogram. This is the result. So when we identify, but the problem is the head loss for orifice diameter. So the friction, the permanent pressure loss as a friction of the measure difference. So we need to use P1, P3, P1 minus P2. So equals 1,250 minus 2,830. This is same equals 0.44. So instruction is the answer of the problem. Instruction we get from above that number one is that the permanent pressure loss as a friction of the matter. Number one is that the final design we get from problem one is dt equals 0.165 meters and beta is 0.66. Because from the problem that we need to get close to target value is 300 millimeter. So we used it to solve it again to make sure the height is closer and closer and closer. So after I write it down, work it and solve it, we get dt is 0.165 meters and the beta is 1.66. And then the instruction number two is that the pressure loss is 0.44. That is the answer. So we begin to the next problem. So we go to the next problem. The next problem is the spray head. Okay, an airflow. So From the equation above, that the spray head is spray heads in an agree. The spray head is an agricultural spraying system are to be supplied with water through 500 feet of turned aluminum tubing from an engine-driven pipe. In its most efficient operating range, the pump output is 1,500 GPM at a discharge pressure not exceeding 65 psig. For a satisfactory operation, the sprinkler must be operated at 30 psig or higher pressure. Minor losses and elevated change might be neglected. Determine the smallest standard pipe size that can be used. Okay, so when we analyze a pipe, when we're analyzing a pipe, that we're using a die pipe again. So the instruction, we need to find the smallest standard. Find smallest standard pipe. Okay, find the small standard pipe. Solve the problem in the name of Allah. Solve the problem in the name of Allah. Okay, we begin to start with initial thinking. Initial thinking. We start with using initial thinking. We need to draw the shape of the pipe. We make it shape like this is a pump. This is the length. This is the pressure release. Key equals 1,500 GPM. This is 2, this is 1. P2 is more than 3 psig, and P1 is less than 65 psig. So L equals 500 feet. Okay. From the data we had, we create from the given data, from the picture is L equals 500 feet, Q equals 1,500 GPM, P1 65 psig, P2 is more than 30 psig. And we knew that eh, P1 max equals 65 um, and P2 max equals 30 psig. Okay, so we begin to create assumption. We assume that assumption we had is the flow is steady flow. Assumption 2 is incompressible flow. From HER equals HI and HEM equals 0. Z1 equals Z2 and V1 equals V2 equals V. So the equation we get from this is HER equals HI plus HIM equals FL per D P squared 2. So we need to convert to equals P1 minus P2 equals F L per D V quadrat per 2. This is the equation we get. This is the equation we get. Okay, this is the equation we get from the assumption above. So the next step we get is idealization. Okay, the next step is the idealization. Idealization. Okay, from the idealization, we start by, we assume that delta P max equals P1 max minus P2 max. Result is 65 minus 30 psi equals 35 psi. But what we need is to find the smallest. This is the max. We need to find the smallest. So from what we get is that from this P1 minus P2 equals FLD free P quadrat 2 per 2. So the next equation we use, okay, the next equation we use, we insert the equation FL per T P per 2 for Q T D quadrat. So the result we get is 8 FLP quadrat per mu P quadrat D pangkat 5. We need to convert Q, must be converted to cubic per second. So from the data we have above, Q equals 1,500 joules per minute times minute per 60 second times feet 7.48 gal equals 3.34 feet per s. So we need to find the Reynolds number using the same equation from the previous problem. RE equals 4Q minus PVD. So what do we get is 4 per P times 3.34 times S per 1.21 times 10 minus 5 times 5.026 in times 12 in per feet. From the equation above, we get the result is 1.06 times 10 6. This is the result we get. So for a draw tubing, E equals 5 times 10 minus using table equipment, and hence ED is 1.5 times 10 square minus 5. So F equals 0.012. So after we get all the data, from analyzing Q, R, E. So we begin to solve the delta P. So the delta P. Okay, so from the previous explanation, we assume we take the nominal is for this, we take the nominal for in, because the RE we get is 1.06 times 10 6 RE. This is the RE result. So when we solve the delta p from using the equation, this equation. So we begin to f lp q quadrat per p squared d5, because this is a long equation. This is really long equation, so I can simplify my work. So it's 8 times p squared times 0.012 times 500 feet times 1.94 times 3.34, and continue the same. This is the same. This is the same times. This is the same as the above. So the result we get is 172 lbf per in squared. This is more than delta p max. So we try using because since the pressure drop is too large, we begin using d equals 6 in. So RA we using to solve it again. We solve it again. P times 3.34 times S minus per 1.21 times 10 minus 5 feet per square times 0.065 in plus 6.065 in times 12 equals 6.95 times 10.5. We begin to use delta P to solve it again using the same equation, because the result I'm going to skip it. So the result so is because from the data above that we knew is that the from the result we had that d d equals 0.012 and d equals 0.012. So there is a specific number for d from d here, and f here is 0.012. Sorry, the f from s from this equation f, we can identify it as 0.012. But in this case, because the because the f is 0.012, 0.012 is from equation d equals 1.5 times 10 squared minus 5. So the f is 0.012. So if the 6 in, the f is the f is 0.013. So the result we had is 24 lbf in minus delta p max. So this is the result we are after, and we're trying to compare it. We're trying to compare it, the result of 6 in and 4 in. So the instruction we get, the instruction from result is that the criterion for pressure drop is satisfied in diameter 6 in. Is satisfied in diameter 6 in. Diameter 6 in. Why the result is correct? So when we compare it again, P1 must not P max. We knew that the must not more than 24. Delta PM is less than 24. Delta P is uh, less than delta PM. Delta PM equals its maximum. This is the maximum. So because it's less, so it's the correct answer. So we begin to the third problem. We begin to get inside the third problem about a dragster. Dragster. Okay. From the dragster weighing 1,600 LBF attained a speed of 270 miles per hour. In the quarter mile, immediately after passing through the timing light, the driver opens the direct chute of area A equals 25 feet. Air and rolling resistance of the car may be neglected. Find the time required for the machine to accelerate to 100 miles per hour in standard air. So uh, the intention we had, okay, the intention, the intention we had, the intention we had is that we need to find time to require the machine reach reach 100 miles per hour. Don't forget solving the problem in the name of Allah. In the name of Allah. Then we begin to go to the initial thinking. Initial thinking. We begin to we need to identify the force that worked on the car. So there is V, the speed V, and there is X. There is V, FD. That's the drag. So the equation we get is FD equals MA equals M dV per dt. So the given data from above, the given data, the given data, the given data equals VO equals 170 mph, VF equals 100 miles per hour, and P equals 0.00238 slug feet. Okay, since CD, so we assume that the CD equals FD per 1 P V quadrat A, then PFD equals half CD P V quadrat A. Then we substitute using Newton's second law. We substitute to Newton's second law. We make the equation is, wait, I need to describe it. Uh, uh, Newton's second law. Newton second law. Here it is, and it becomes negative half because the Newton's second law that there is a negative force. So the half CD, CD, salah. The negative CD P V quadrat A equals M dV per dt. This is the equation of the Newton's second law from FD. So we begin to, this is the equation. So now we can move to idealization. From the idealization, we can begin to use idealization. We can begin by separating variable and integrand. We obtain No, 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 no. No, 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 no. Okay, then we move it again. Then, okay, no, 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 no. This is the equation of the Newton's second law. So we go to idealization, idealization. Uh, by using the Newton's second law, we separate variable and integrating, we obtain minus one CD P A per M equals TO dt equals VO dV per V quadrat. From that, we can simplify. We can simplify it, becoming T equals VO minus VF per VO times 2M CDPA. So what we get is T equals VO minus VF per VF VO times 2W CDPHG. Now, this is the equation we get to find a T that required to reach the speed. So the speed is 100 miles per hour. So we insert the data. So the T equals 270 minus 100 miles per hour times 2 times 1,300 lpf times 100 miles per hour, times half hour, 270 miles times 1 per 1.2 times feet, 0.00238 slug times 125 feet times S quadrat 32.2 feet times slug dot feet LBF dot S quadrat times ME 5,280 feet times 600 S per hour. So what we get is that we can begin to erase it. There is a slug here, minus coret-coret. LBF is here, coret-coret. ME, coret-coret. Hour, coret-coret. Uh, hmm, miles, coret-coret. So the result we get is time 0.05 seconds. This is what we get, the time that we need. So we begin to assume that, so the time is 5.05. So we begin to get the instruction. Then we find it. So the time needed to reach speed 100 miles per hour is 5.05 seconds. This is the result instruction. Now we begin to next about from the next problem. So if I heard it correctly, This is how can we describe to find the equation that happened here. Okay, from this we can assume that if I read it correctly, that this number is discussing about. Wait for a second. I need to read it. So the intention about the problem is that intention is that I want to about flow about find out about open channel flow and channel works and find out to solve the problem. Found out to solve the problem. To solve the problem. Solve the problem. And the different at relative coordinate at relative coordinate. So and we cannot forget that we solve the problem in the name of Allah. In the name of Allah. Allah subhanahu wa ta'ala. So from the picture above, I don't need to draw it, but it's explained a lot that in absolute coordinate, the fluid moving at speed here. And the difference between the coordinate address relative to wave and absolute coordinate is that uh, when the fluid is moving, the fluid moving at speed is here. So the absolute coordinate, the fluid moving at speed delta v, and the fluid moving at speed is c times delta v, the fluid moving at speed c. So why is it the fluid moving at speed is c minus delta v? It's because when we operate this problem, we get that c is moving against the absolute coordinate. So the equation for fluid mechanics at speed is c minus delta v. So we begin to initial thinking. Initial thinking, we begin by making assumption or the given data. But the given data is already, it's not solving a problem, but we need to find how does it work? Initial thinking, initial thinking, initial thinking. Initial thinking, we had that assumption we make in that picture is that assumption is a steady flow. Is a steady flow and incompressible flow, uniform velocity, hydrostatic pressure distribute at each section. Hydrostatic pressure distribution at each section, and frictionless flow. Frictionless flow. Okay, so we begin to idealization. So we begin to insert idealization. Um, Idealization. Okay, idealization that the flow, uh, incompressible with uniform velocity is delta CSV equals 0. Applying to the control volume, control volume, control volume, we get that C minus delta V Y plus delta Y B minus CYB equals 0. So the delta V equals C delta Y plus delta Y. For a momentum equation, with a momentum equation, again with the assumption of uniform velocity at each section, we use following form of the x component of the momentum. So the momentum equation is Fx equals Fsx plus Fbx equals dy dt Cv OP dA plus Cs UP V delta A. So this momentum equation is the same as when we try to solve the problem number 2. Number one. Here it is. Here it is. Wait, which number again? Uh, okay. Uh, from this, we need to make add more page. So this is the equation. But the unsteady term of d per dt disappears as the flow is steady. The force Fb is 0 for horizontal. So we obtain that because it's steady, the result that we find is Fsx equals CCS up VA. This is what happened when the flow is steady. The flow is steady. And when the and that is how you solve the problem. So to so the surface force consists of pressure force on the two ends by assumption 5. We neglected friction. The gauge, so the neglected friction. So the gauge pressure at the two ends is hydrostatic, as illustrated in the figure above. Here, the figure here. So the hydrostatic force Fr on submerged vertical surface of area A is given by simplest result. So the gauge pressure is FR equals PCA. This is the equation. So after that, we get into the instruction. From the instruction, we try to solve the problem, the answer of all the above. So every assumption we make, there will be a change of the equation. So the control volume, so the control volume we have is delta V equals C delta Y per Y plus delta Y. And the momentum equation is equation from assumption above, above, from assumption above is FSX equals UP 2P V delta. Okay. So, and because the four wave of delta small amplitude, we can simplify the expression to C equals G. What? G. Now we get to the final questions. Okay. The airflow isentrope. The airflow isentropically is an oh, the airflow is entropically through converged nozzle at a section where a nozzle area is 0.013 feet squared. The local pressure, temperature, and Mach number are 60 psi, 40 Fahrenheit, and 0.52 respectively. The back pressure is 30 psi. The Mach number at the throat, the mass flow rate, and the throat area are to be determined. So from this, we need to find from the intention we begin to using die 5 is that we identify it. The intention is find the Mach number at the throat, the mass flow rate, and the throat area. Okay, find the Mach number at throat, Mach number at throat. This is problem one. Problem two is to find the mass flow rate. Find the mass flow rate. The mass flow rate. This is problem number two, and the problem number three. Determine the throat area. Determine the throat area. The throat area. So, and we don't forget that we solve the problem in the name of Allah. We solve the problem in the name of Allah. So, from the perspective we had, now we move to initial thinking. initial thinking, we describe it, the given data. The given data is this. The given data. The given data is the given data. Okay. The given data is M1. Oh, sorry. The given data is M1 equals 0.52, T1 is 40 degree Fahrenheit, T1 is 60 psi, and A1 is 0.013 feet per second. So to make it simpler, we draw the picture. This is phase one. This is phase one. This is T. So the flow is here, flowing. Then we can determine that first we check first checking to determine if flow is isentropic down to PB to check if we avoid the stagnation condition. So we need to evaluate stagnant condition. Ready? We need to use stagnation equation. Stagnation equation is condition is PO equals P1 plus K min 1 plus M1 kuadrat Q per K min 1. From this, we can identify it to search the stagnation condition. So from the diagram above, we can see that there's a structure. It looks like structure. So from what I learned is that there is this is PO, this is TO. From the picture above, PO and TO, and this is T1, this is P1. This is P1. And continue, and keep continuing, and keep continuing. This is PB, T2, T, PT. It will continue to go down, upwards. So T, S. Okay, after that, we can search for the mass flow rate. We need to find mass flow rate, V1 equals M1, C1 equals M1, K, R, T1. This is a mass flow rate equation. This is stagnation condition. So we can identify the choke flow. For the choke cut flow equation is A, T equals A. So this is the equation we need to solve the problem. These three problems. There is a three. So there is a three equation. This equation, this, and this. Now we begin to idealization. From idealization above, we use the stagnation equation. So the stagnation equation is PO equals P1. Here is K min 2 M1 square times square K per K min 1. So we begin to insert the equation. The P1 we got 60 P, yeah, this is P, sorry. So 60 PSI, PSI times 1 plus uh, so we can determine that plus 0.2 times 0.52 squared 3.5 equals 72 CA. So PB per PO equals 30 bagi 72. So we had 0.417. It's less than 0.528. So the flow in choke. So the brake pressure. This is the brake pressure ratio. Brake pressure ratio. So the flow, the the flow choke is choke. So MT equals 1.0. From the TS diagram, we can assume that now we begin to find the mass flow rate. Mass. So flow MT is 1. This is from the perspective of the problem is to find the main number of the throat. That's the first. So because the throat is 0.4417, we simplified it to become 1. So the Mach number of the flow choke is 1. So the mass flow rate, we begin the equation using section 1, using P1 V equals berarti V1 M1 C1 equals M1 times TRT1. So we substitute it, M1 is 0.52, 1.4 times 53.3 times 460 plus 40 air plus 32.2 times, sorry, see that one again here, F F air air R times 32.2 times, eh, wait, LBM slug, times slug FT per LBF times S quadrat. The 53.3, there is feet times LBF per LBM times R. Okay, well, before we resolve, we need to identify it. So we need to write it apus, erased, and there is a slug. This is slug 2, and feet, feet stays, and R is disappeared. LBF disappeared. So the rest is, so the V1 we get is 500 feet per second, because feet times feet is feet quadrat per S quadrat. We can identify like that. So the V1 we get is 570 feet per second. The next is we need to find P1. Oh, sorry. To find flow rate, we need to use not this equation, but we need to use M P1 times V1 times A1. This is we need to use to solve the mass flow rate. So the P1, so the P1, so the P1 equals P1 per RT1 equals 60 lbf per in quadrat times lbm 53.3 feet lbf times 1 plus 500 r times 144 in 1 feet quadrat. So like the previous step, we need to hapus. We need to erase it. So LBF cannot be used. R cannot be used. In quadrat cannot be used. In square cannot be used. So what left is LBM and fit. LBM and fit. So the result we have from the equation above is 0.324 LBM per fit pangkat 3. Ini dia. Soal ini fit pangkat 2, ini fit. Berarti jadi fit pangkat 3. Selanjutnya kita sudah, kalau kita semua data sudah terkumpul, when the data is already being gathered, we need to use mass flow rate equation equals P1 V1 A1 0.324 lbm per feet times 570 feet per second times 0.013 feet per square. Because this is done, done. So what left is lbm per second. So the result we have ME equals to 40 lbm per second. This is M result. So this is number 1. This is number 2. Now this is number 3 problem. Okay, this is a number 3 problem. From equation that A1 plus A equals 1, M1 equals 1 plus K minus plus 2, M1 squared, K plus 1 per 2, we get K plus 1, 2K minus 1. Then we can insert the data to solve the problem. This 1 equals 0.52 times 1 plus 0.2, 0.52 squared per 1, 2 is 3.00. The result we get is 1.303. So the force choke flow from the equation above, that the choke flow is 80 equals the choke flow is 80 equals A. So equals A1 plus 1.303 equals 0.013 feet per square, 1.303. So the AT equals 9.98 times 10 feet squared. So the result is 80. So the instruction we get is wait, the instruction we get that from the equation above, that the Mach number at the throat, the Mach number on the throat, on the throat is, the equation is one. The 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 mass flow rate, the mass flow rate the mass flow rate is 2.4 lbm, is 2.4 lbm. And finally uh and finally the choke the choke at the throat area, at the is 9.98 times 10 squared minus 3 feet per square. So this is all I can explain about my exam all about mechanical fluids. Thanks for watching. Uh, make, make sure you stay conscious, and thank you for Mr. Dai, who teach me about Dai 5 so that I can understand more about how to solve problem correctly. Kurang lebihnya mohon maaf. Wassalamualaikum warahmatullahi wabarakatuh.